Right now, something remarkable is happening in the darkness beyond everything most people imagine when they think about our solar system. More than 20 billion kilometers from Earth, where sunlight has faded into little more than a distant glow, a machine no larger than a small car continues a lonely journey. No astronaut can reach it. No engineer can repair it. No rescue mission could ever catch up with it. Since 1977, it has traveled farther than any human-made object except its twin, leaving behind every planet, every familiar landmark of our solar system, and finally crossing into the vast unknown between the stars. But before we continue this incredible journey, if you enjoy real stories backed by science and want to explore more mysteries of the universe, please take a moment to subscribe to the channel and help us reach 1,000 subscribers. Your support allows us to keep bringing you carefully researched stories like this one. Now, there is another part of Voyager 2's story that makes this moment even more extraordinary. The spacecraft is slowly running out of life. Every year, it loses about 4 watts of electrical power. One by one, the instruments that have spent decades exploring the cosmos are being switched off forever. Yet, despite its age and failing power supply, engineers at NASA refuse to let its mission end. Instead, they are preparing one of the boldest engineering maneuvers ever attempted on a spacecraft nearly half a century old, a last effort they call the Big Bang. Why fight so hard to keep an aging spacecraft alive? Because what Voyager 2 has revealed about the edge of our solar system has transformed our understanding of the universe. It has uncovered the invisible shield protecting every planet around the sun, explored the violent frontier where our solar system collides with interstellar space, and returned measurements that no other spacecraft has ever been able to collect. It is one of the greatest scientific stories ever told, yet surprisingly, few people know it in full. This is the real story of Voyager 2. There is no fiction here, no exaggeration, only discoveries confirmed by decades of scientific research. And the truth is even more astonishing than fiction. To understand why Voyager 2 matters so much today, we have to return to where its journey began. On August 20th, 1977, a rocket lifted off from Cape Canaveral, Florida, carrying Voyager 2 into space. Just 16 days later, its twin, Voyager 1, followed. These 2 spacecraft were built for a once-in-a-lifetime opportunity. Astronomers had realized that Jupiter, Saturn, Uranus, and Neptune would soon line up in a rare planetary alignment that occurs only once every 176 years. Such an alignment would allow a single spacecraft to visit all 4 giant planets by using each world's gravity as a giant slingshot, gaining speed with every close encounter before racing onward to the next destination. The idea became known as the Grand Tour. It had first been proposed in 1964 by NASA scientist Gary Flandreau, who recognized that this extraordinary alignment could dramatically reduce travel time across the outer solar system. Without it, reaching Neptune alone would have required roughly 30 years of direct flight. By taking advantage of the gravitational slingshots, Voyager 2 completed the journey in only 12 years. The opportunity was so rare that, once missed, it would not return until the year 2153. NASA chose to seize it. What followed would change planetary science forever. When Voyager 2 reached Jupiter, scientists expected to learn more about the largest planet in the solar system. Instead, they discovered something nobody had confidently predicted. On Jupiter's moon, Io, Voyager found active volcanoes erupting across the surface, the first active volcanism ever observed anywhere beyond Earth. Until that moment, Earth had been the only known world with active volcanoes. In a single discovery, Voyager 2 revealed that our solar system was far more dynamic and geologically alive than anyone had imagined. For more than 4 decades, Voyager 2 continued its silent journey away from the Sun. With every passing year, the solar wind grew weaker, spreading farther and farther into space, until, at last, it reached the point where it could push no farther. Racing outward at hundreds of kilometers per second, the stream of charged particles from the Sun finally lost its momentum. Ahead lay something entirely different: the interstellar medium, an ancient, cold plasma that fills the immense distances between the stars. The boundary between these two regions is known as the heliopause. Crossing it means leaving the Sun's protective bubble and entering, by every meaningful definition, the space between solar systems. On November 5, 2018, after 41 years of uninterrupted flight, Voyager 2 reached that boundary. It crossed the heliopause. Only one spacecraft had ever done it before: its twin, Voyager 1, which had entered interstellar space on August 25, 2012. But Voyager 2 carried one critical advantage. Unlike Voyager 1, whose plasma science instrument had stopped working in 1980, Voyager 2's plasma science experiment was still fully operational. That instrument could directly measure the temperature, density, and speed of charged particles surrounding the spacecraft. For the first time in human history, scientists were not simply estimating what happened at the edge of the solar system. They were measuring it directly. What Voyager 2 discovered surprised almost everyone. In November 2019, 5 separate research papers published simultaneously in Nature Astronomy revealed the spacecraft's findings from its historic crossing. For decades, scientists had expected the heliopause to be a broad transition zone, where the Sun's plasma slowly mixed with the plasma of interstellar space across a vast region. Instead, Voyager 2 found something remarkably different. The boundary was far thinner and far sharper than theory had predicted. Rather than blending together gradually, the hot, thin plasma carried outward by the solar wind met the colder, denser plasma of interstellar space, almost like two different fluids colliding against each other at a distinct interface. Don Gurnett, the University of Iowa physicist who led the plasma wave instrument team, compared it to a cold front in Earth's atmosphere, where a mass of very cold air meets much warmer air moving in from the south. It was not a gradual fade, it was a boundary. That single discovery immediately changed scientists' understanding of the heliosphere. The measurements revealed an enormous jump in plasma density. Inside the heliosphere, Voyager 2 measured only about 0.0002 particles per cubic centimeter. The moment it crossed into interstellar space, that number rose dramatically to approximately 0.039 particles per cubic centimeter, around 20 times denser. That difference is what creates the heliopause itself. The heliosphere is essentially a vast bubble of hot, fast-moving solar plasma pressing outward against a colder, denser, and slower sea of interstellar material. The two regions do not gradually blend together. They press against one another, forming a real physical boundary. Yet even that remarkable discovery was not the mission's greatest surprise. The biggest revelation came when Voyager 2 measured the temperature of the plasma surrounding the heliopause. The instruments reported a temperature of approximately 50,000 Kelvin, around 50,000 degrees. That is roughly 10 times hotter than the surface of the Sun. Finding temperatures like that at the very edge of the solar system, in a region long expected to be cold and quiet, completely changed scientists' understanding of this distant frontier. Many researchers describe it as a wall of fire surrounding our solar system. Fortunately, despite those extraordinary temperatures, the plasma is so incredibly thin, containing only a tiny number of particles in each cubic centimeter, that a spacecraft can pass through it without suffering damage. The particles themselves carry tremendous energy, but there are so few of them that they cannot transfer enough heat to harm the spacecraft. What Voyager 2 revealed was that the heliopause is anything but peaceful. It is a turbulent, energetic collision zone where powerful plasma interactions are taking place continuously at the very edge of our Sun's influence. And that discovery raises an even bigger question. What does all of this mean for Earth? As Voyager 2 continued sending its discoveries back across billions of kilometers of space, scientists gradually realized that its findings were about far more than the distant edge of the solar system. They were also about home. Most people never think about the invisible shield surrounding our solar system, yet every moment of every day, it is protecting Earth. This vast bubble, known as the heliosphere, stretches far beyond the planets, carried outward by the solar wind. After traveling through it for more than 4 decades, Voyager 2 became the first spacecraft capable of measuring its outer boundary directly, revealing how this enormous protective shell truly behaves. What the mission confirmed is remarkable. The heliosphere shields the planets inside it from roughly 70% of the high-energy cosmic rays constantly streaming through interstellar space. Those cosmic rays are born in some of the most violent events in the universe. They are produced by exploding stars, the winds of pulsars, and the powerful relativistic jets launched by black holes. Traveling across the galaxy with enormous energy, they are capable of damaging biological tissue and disrupting genetic material. Earth has its own defenses. Our atmosphere and magnetic field provide additional protection. But the heliosphere is the first and largest shield, standing between our planet and the radiation-filled environment of the Milky Way. That is why understanding its true nature matters so much. Knowing exactly how thick this protective bubble is, how sharply its boundary is defined, and how it responds to changes in the Sun's activity is not simply an academic question. It directly affects our understanding of the conditions that allow life to exist on Earth, the safety of future human missions into deep space, and even how planets elsewhere in the galaxy might remain protected from their surrounding radiation environments. Because Voyager 2 crossed the heliopause with its scientific instruments still operating, it refined our understanding of this protective barrier in ways that no telescope or remote observation could ever accomplish. Yet, just as the mission was delivering some of its most valuable discoveries, another story was quietly unfolding. It was a story of time. After nearly half a century in space, Voyager 2 was beginning to run out of power. For NASA's engineers, preserving the mission became more than an engineering challenge. It became a race against an unstoppable clock. Like its twin, Voyager 2 is powered by a radioisotope thermoelectric generator, a device that converts the heat produced by the natural radioactive decay of plutonium-238 into electricity. It carries no fuel tank waiting to run empty. Instead, its power slowly fades because radioactive decay never stops. Year after year, the plutonium produces slightly less heat, and every year the spacecraft loses approximately 4 watts of electrical power. 4 watts may sound insignificant, but over 47 years, the losses have steadily accumulated. Voyager 2 began its journey with roughly 470 watts of electrical power. Now, every remaining watt has become precious. The spacecraft's scientific instruments continue drawing electricity as they perform their observations, but the available power keeps shrinking. Something has to give. NASA's response has been careful, deliberate, and, in many ways, heartbreaking. One by one, the spacecraft's instruments have been switched off to preserve enough electricity for the mission to continue. Each Voyager originally carried 10 scientific instrument packages. Today, 7 of them have already gone silent. On February 25, 2025, engineers at the Jet Propulsion Laboratory shut down Voyager 1's cosmic ray subsystem experiment. Less than a month later, On 24th March 2025, they sent another command across nearly 20 billion kilometers of empty space to Voyager 2. Its low-energy charged particle instrument, which had measured ions, electrons, and cosmic rays from across the solar system and the galaxy almost continuously since 1977, was turned off. 48 years of uninterrupted scientific observations ended with a single command transmitted across the darkness of interstellar space. Then, on April 17, 2026, NASA also shut down Voyager 1's low-energy charged particles experiment. Even so, Voyager 2 continues working. Its magnetic field instrument and plasma wave instrument remain active, while its cosmic ray subsystem is scheduled for shutdown during 2026. The decisions have never been easy. Mission Project Manager Suzanne Dodd explained the reality with complete honesty. If they had not turned off instruments, the probes would probably have had only a few more months of power before NASA would have needed to declare end of mission entirely. Those words captured the difficult balance facing the team. Every instrument switched off means losing a scientific capability forever. Yet every instrument sacrificed also gives Voyager 2 a little more time to continue exploring the unknown beyond the edge of the solar system. But despite the steady loss of power, NASA is not ready to let Voyager 2 fall silent. Not yet. As long as there is even the smallest chance to extend the mission, the engineers are determined to take it. That determination has led to one final engineering gamble. In 2026, the team prepared a maneuver with a name that reflects both its boldness and its desperation. They called it the Big Bang. The idea itself is surprisingly straightforward, but carrying it out on a spacecraft that has been traveling through deep space for nearly half a century is anything but simple. Voyager's attitude control thrusters rely on fuel lines that must remain warm enough to function. To prevent them from freezing, the spacecraft uses electric heaters, and those heaters consume valuable electrical power every single day. The Big Bang maneuver aims to change that balance. Instead of allowing the heaters to continue drawing electricity, engineers plan to switch them off completely and reroute power from 3 other onboard systems in a carefully calculated effort to keep the fuel lines warm by redistributing the spacecraft's limited energy resources. If successful, the adjustment could free enough electrical power to keep at least one additional scientific instrument operating for another year or possibly even longer. It is an elegant solution. It is also an extraordinarily risky one. Nothing like it has ever been attempted on either Voyager spacecraft. If the strategy fails and the fuel lines become too cold, the thrusters may stop working. Without functioning thrusters, Voyager 2 would no longer be able to maintain its orientation or keep its antenna accurately pointed toward Earth. And once its antenna turns away from our planet, the spacecraft will fall permanently silent. For that reason, NASA chose to begin with Voyager 2. It still has slightly more electrical power available than its twin, and, at a distance of approximately 20 billion kilometers from Earth, is a little closer than Voyager 1. That shorter distance makes communication slightly faster and reduces the overall risk of testing the new approach. The first tests are planned for May and June 2026. If everything performs as expected, the same maneuver will be attempted on Voyager 1 no sooner than July 2026. Should both spacecraft survive the procedure, NASA's engineers believe each probe could continue returning data with at least one operating scientific instrument well into the 2030s. It is an extraordinary thought. These spacecraft have endured the harsh environment of deep space for almost 50 years. Many of the engineers now working tirelessly to preserve them had not even been born when Voyager 2 began its journey. Today, they are maintaining machines designed before the personal computer became part of everyday life. They are operating software written in programming languages that few engineers still use, sending commands across distances so immense that even light itself requires more than 18 hours to reach Voyager 2. Only after waiting another 18 hours can they know whether the spacecraft successfully received the command. Every decision becomes a 37-hour exercise in patience. Every maneuver becomes an act of faith. Yet despite all of that, Voyager 2 continues to answer. Its signals arrive slowly, almost delicately, at a transmission rate of only about 160 bits per second. The data stream is so limited that transmitting a single low-resolution photograph would require hours. But the information keeps arriving. Its magnetic field instrument and plasma wave instrument continue measuring the interstellar medium surrounding the spacecraft, recording changes in plasma density, mapping fluctuations in magnetic fields, and studying a region of the Milky Way that no human instrument has ever explored directly. The observations Voyager 2 is making cannot be collected anywhere else. No other spacecraft is there. No planned mission will reach that distance for decades. Every measurement Voyager 2 sends home is unique. Every remaining day of operation expands humanity's understanding of the galaxy in ways that cannot be repeated. And then there is one final detail. Perhaps more than anything else, it reminds us what Voyager 2 truly represents. Bolted securely to the side of the spacecraft since its launch in 1977 is a remarkable object known simply as the Golden Record. It is a 12-inch gold-plated copper disc created to tell the story of Earth. Stored upon it are 115 images encoded as analog signals. It carries the sounds of rain, crashing waves, wind, thunder, and birdsong. It preserves 90 minutes of music chosen from cultures around the world. It includes greetings spoken in 55 human languages, alongside the haunting call of humpback whales. It also carries recorded messages from United States President Jimmy Carter and United Nations Secretary-General Kurt Waldheim. The Golden Record was created under the leadership of Carl Sagan and a small team of scientists and artists who understood the significance of Voyager's journey. They realized that this spacecraft would become humanity's first physical ambassador beyond the solar system. The record was never intended to be recovered. It was created to travel endlessly through the Milky Way, carrying with it the sounds, images, music, and voices of a civilization that once existed on a small rocky world orbiting an ordinary star, waiting, perhaps forever, for someone, somewhere, to discover it. The Golden Record was never meant to come home. From the moment Voyager 2 left Earth in 1977, its creators knew that no one would ever retrieve it. That was never its purpose. Instead, they imagined something far more enduring. Bolted to the side of the spacecraft, the record was created simply to exist, to journey endlessly through the Milky Way, carrying with it the sounds, images, music, and voices of a civilization that once lived on a small rocky planet orbiting an ordinary star in one of the galaxy's outer spiral arms. It was intended to continue that journey for as long as it might take for something, somewhere, to one day discover it.